Now that we looked at different types of intersection, we now not only want to look at the intersection of lines and planes, or two planes and so on, we want to look at the angle that these two components of vectors form. So we will look at three different situations. We will look at the angle between two planes, the angle between two lines, and the angle between a plane and a line. So the equations are fairly simple, and you just need to know which ones to use in which situation. So in general, let's look at the angle between two planes. If we look at the diagram on the right, you can see that if two planes intersect, they will form four angles. Two of them will be equal obtuse angles, and two of them will be acute angles. So we will get different angles, and the question is, which one do we actually use? Well, if you notice, it's much better to actually look at the normal of each vector and consider that as our starting point to find the angle between the lines. So if I have this normal and this as my normal, the angle that they form will represent the angle between the planes. So in general, we tend to take the acute angle as the angle between the two planes, just to keep that in mind. So how do we actually find it? Well, we already have the tool to find it. We use the scalar product formula. We know that going back to scalar product, we know that the scalar product of two vectors is equal to the magnitude of each one multiplied by cos theta, where theta is the angle between them. So we're not taking the equation of the plane, we're taking the normal of the plane and the angle between them, and the diagram explains why. Because this will be theta, theta, and then you have theta here, so that's the acute angle we're considering. Now, to get that acute angle, we need to make sure that our equation is set up nicely. So in order to be able to get that acute angle as an answer, we need to take the absolute value of the numerator, which is the scalar product. Otherwise, if it was negative, then it would give you answers in the second and third quadrants, and that's not what we want. So we're looking at the absolute value of the scalar in the scalar product of the normals of the plane divided by the magnitude of each plane. Now the magnitude is already going to be positive, so we don't need to worry about the denominator. In general, if you see the formula for the equation of the angle between the planes and they don't have these absolute value lines, you can assume that you need to take the absolute value of the numerator. So let's start with an example here. We have two planes and I need to find the angles in radian between them. Well, I need to actually know the normal of the two planes. So the normal of the first one is just me taking the coefficients here, so 1, 2, and minus 2. And the normal of the second is going to be 2, minus 3, and minus 6. And you can immediately put everything into the formula, so you can start with just doing a cos inverse and then writing out the scalar multiple of this, the scalar product of these divided by and so on. Or you can do the scalar product separately, up to you, just as long as whatever you're substituting in the formula is correct. So I am taking the scalar product first and taking the absolute value of it. This will give me 2 minus 6 plus 12, which is already a positive number, 8. So I know my numerator is going to be 8. My denominator is basically the magnitude of each. So that's 1 squared, 2 squared, minus 2 squared. And then the other one, making sure they're in separate square roots, plus minus 6 squared. This will simplify to 21. And you just need to put this in your calculator, especially if it's a calculator question. So this will just give you 1.18 radians. That's the 3 significant figures. So it's fairly simple. The only thing that the calculator will help you with is taking that cos inverse. Unfortunately, there's no method to actually find the magnitude of these. You have to manually do it. So you just have to use this last line. And again, as I said, you can completely plug this part into the numerator, but I'd rather do it separately to avoid any mistakes. Now, what if I have two lines and I need the angle between them? So same idea as before. So to find the angle between two lines, we do the same thing except that we take the direction vector of the two lines. So I have direction vector 1 and 2, and then I need to take, again, the absolute value here and cos inverse of them. So let's try that with this example. So the direction vector, remember, is the values here. You can rewrite this in vector form just to make sure that you get the direction vector correctly. So the direction vector of line 1 is going to be 3, 4, and 12. Now for line 2, just be careful because you have 2, but then I always say take the denominator, which might seem to be 1 here, but this is a negative y. So in reality, this is 1 plus 5 over minus 1. This is what it actually is. So minus 1, minus 2. Then you have these two, and again, the equation follows the same method. So I can take the scalar product of these two and take the absolute value of them. So this will, I'm going to skip writing all the numbers. This will give me a negative 22, so I need to take the positive 22 here. And then writing out the formula, I have cos inverse of 22 in the numerator, and then I need to take the magnitude of each one. And just plugging this into the calculator simplifies to this, which gives me 0.971 radians, and that's the 3 significant figures. And then lastly, we look at a line and a plane. Now this is slightly different. If you look at how they behave, so first you need to make sure that the line is not parallel, nor is it on the plane. So that's one thing we need to check in the beginning. So otherwise there is no angle between them. So if they're not parallel, they're not on the plane. So we're looking at a line that has a point of intersection with your plane. So looking here, I can see that I can find this angle. Well, if I take what we did similarly, which is the direction vector and the normal, it will give me this angle, which if I consider this as a right angle triangle, this is vertically opposite, so this is also theta. So the formula will give you, using the formula, I can use the direction vector and the normal, and that's going to give me theta. However, theta is not the angle that's between the line and the plane. It's phi that's the angle between the line and the plane. So this formula, what we've done so far, will actually give me this angle, and what I need is this angle that they have here. So how do I find that? Well, keep in mind that if you look at the way the triangles form, if this is theta, this is 90, then this angle will just be 90 minus theta, which is one way to solve the questions. Is if we know this fact, we know that it's 90 minus theta, well, you can use the same formula, and then once you have the answer, you just take an extra step and you go 90 minus theta. But there is another fact that we know. We know that sine x is the same as taking cos 90 minus x, and I'm talking about degrees here, even though we're going to solve this in radians most of the time. But sine x is the same thing as saying cos 90 minus x. We know this fact about sine and cosine. So actually, to make our lives easier, in order to find the formula, instead of doing this extra step of 90 minus theta unless we find the answer, instead of what we can do is instead of taking cos inverse of our equation, we take sine inverse of our equation. it will give us the equivalence of doing this 90 minus theta. So just for a line and a plane, you take the sine inverse of the equation. So let's have a look here. First, part A wants you to find the point of intersection between the line and the plane. So this just confirms that the line is not parallel, nor is it on the plane. So I will do this very quickly because this is already discussed in another video. We write this in parametric form. Plus 2 lambda, 5 plus 4 lambda. Now I want to discuss how you need to just be careful here. You notice that it's 3z plus 3 over 2. Remember that this is equal to lambda. So what we're trying to do is make z the subject. So once you have z the subject, it's actually going to give you a -1 plus 2 over 3 lambda. So just be careful when your x, y, and z are not on their own. Then we substitute into the plane here. So we replace each x, y, and z with these values. And the lambda should not cancel out, assuming that they will intersect. If it cancels out, then there's no point of intersection. We've discussed that before. 3 lambda, and it's equal to 2. Now I'm not going to go through the math. When you simplify it, you end up with lambda equal to 3. So once lambda is equal to 3, I replace it back into here, and I end up with an x, the point of intersection being 3, 17, and 1. So I found my point of intersection. It's just a matter of replacing the 3 into here and simplifying. Now that I proved that there's a point of intersection, I need the angle between the line and the plane, and we find it as we've discussed before. So you need the direction vector, which is 2, 4, and 2 over 3. So 2, 4, 2 over 3. Now you can take a parallel to this. So I can take a factor of 2 over 3 out, or consider it as a scalar multiple, take any parallel vector to this just to make it look nicer. But you don't need to. This still works. And then you need the normal vector, which is 5, -1, and 4. And we follow the same thing, except that we need sine inverse of our formula. So I'm just going to do the direction vector with the normal, and that's going to give me a 26 over 3. So 26 over 3 goes in the numerator. Denominator will be as follows. And I need to make sure that I'm taking sine inverse. Now, if you take cos inverse, just make sure that you do the 90 minus the answer, or because we're in radians, you'll have to do the pi over 2 minus the answer. But in this case, we will get the same answer, which is 0.300. That's to 3 significant figures. So hopefully the method is easy to follow and it's clear. You just need to remember which equation to use for which situation. This is a nice summary. So if you have, notice how it doesn't have the absolute value in the numerator, but you can easily realize that you have to put it there. So the angle between two lines, you take the angle between the direction vectors. If you have an angle between two planes, you take the angle between the normal. And if it's a line and a plane, you take the direction vector and the normal, and then 90 minus 5. Or you could just do sine theta. So just make a note of this. If the line and the plane are given other forms, we transform them into these just to make it easier to solve the questions.